we are very happy to have one of our own faculty from LA City College, Professor Michael Farrell, who has been in the district now since about 2009, I believe, and teaches geography, which at City College, and all of you who know the geography program, is both human geography and physical geography. So it is, in a sense, the you could say it's the mother hen that laid all the little polluelos. So many disciplines have come out of geography, including urban planning, ecology. So it was the original mother discipline, and that's why I'm always happy to host and talk about geographers because it's a natural interdiscipline. It allows you to look at a natural phenomenon and a social phenomenon all in the same paragraph, and that's really why I like teaching geography as well. So Mike Farrell's been with us for since 2009. And I want to share with you, let's see if I can go to that. Voila. And this is our flyer for the day. And so we haven't quite put a title on this, but the topic is going to be water, because among his many specializations, Michael Farrell is actually a hydrologist and understands the dynamics of surface water movement. And as you all know, we have in Gold Creek, what you could say a creek runs through it. So I was very happy to attend a Gold Creek event some weeks ago where Michael Farrell showed us how to do calculations of stream flow depending on the season, how you look at the sorting of the material in the stream bed, and what is quick, what are the ones that move quickly, the ones that move slowly, and you get a real sense of how streams change and how they even change their directions. What do floods do? How does the vegetation thrive from the water that's in those creeks? And we were treated to a really, really good talk. Um, so that was before the what you're seeing in the flyer, which was actually the open house day we had, and then that I'll share that with you in a second. And then, of course, today this talk on water. And come on, Apple, give me the next picture. Oh, I know you can do it. This is Eaton Canyon, and Mike Farrell took his students on a hike of Eaton Canyon. This, I believe, is prior, of course, to the horrible fire of January. But those of you familiar with Eaton Canyon would also be pleased to know that we had on open house day a hyperlocal meteorologist from Altadena who explained to us the dynamics of that fire. So there is a lot in our district to learn in terms of the physical geography and the natural hazards of the Los Angeles basin, including floods and fires and major changes. And you can see this is the very successful field trip that students took with Mike Farrell. And the other thing, let me see, I'll stop that share, or maybe it'll let me change the topic. Let's see, here's Chrome. This is the geography program at LA City College. And this particular page is very useful because it actually goes through what are the learning outcomes for the program and what are the possibilities in employment and in income from having concentrated areas of study in the earth sciences. So you can see the careers involve atmospheric, earth, marine, space, and that is why I'm really happy that we have Mike Farrell here today, because it gives you an idea of how valuable it is to have geography programs that are healthy and up and running. As you might know, some universities have cut back their geography programs, considering it sort of an outdated 19th century discipline. They couldn't be more wrong. It's probably more needed now, and what we call geographic literacy is something that young people really need. And thanks to Michael Farrell, they are in fact learning that. So the other thing I want to share with you is our website, and then I'll let Michael take over. This is the SEI-LACCD.net website. So the Sustainable Environment Institute has this website. Our homepage, this is the first page, has links to Gold Creek in this case, because we are very happy to be able to host a lot of what Gold Creek wants online. So this was the open house flyer, and then all of the site reports that are produced by the Gold Creek coordinators are actually on this site, the most recent one being April. So that's a really good, they're very well produced. They're very very well laid out, and it has studies of what's happening with the botany and with the flora and fauna. And that's really a very welcome thing that we like to host on our website because it is so valuable to share. And then let me see, go back here. And this was from previous open houses. So faculty have more access to Gold Creek now than they've ever had. There's Rob West and Michael Farrell explaining to people what this is, the facility there, and it's in very good condition thanks to the coordinators. These are the stop motion cameras that even spotted a mountain lion. So with that, I'm going to stop my share and let Michael Farrell take over. I will make a quick change here. Let's see, remove that spotlight and spotlight Michael Farrell, and voila. Um, Thank you, Michael.
Excellent. Well, thank you, George, for that introduction. It's great to see so many of you joining on here. A few faces I know and a lot I don't. So hopefully I'll be able to tell you something maybe new and interesting about water in California. And one thing I'd like to kind of preface this with is hopefully I'm giving you some information to help analyze some of the questions we might have contemporarily of, is Southern California a good place to be living? Is it a good place to be having, 13 plus million people in an urban area, given the needs of that society? And so in kind of weaving together a story of where our water comes from and what impacts occur because of our movement and kind of transformation of our hydrology within California, it can add kind of some bits and pieces to that story. So I'm going to go ahead and share some slides here. And give me a moment and let me know. All right, so it looks like we have a slide that says geographical perspective on water. And yeah, thanks, George, for really introducing geography. And I am certainly going to draw on the different aspects of geography. I think that water and climate are a couple aspects of geography that really are the nexus of the physical and the cultural. So hopefully, whatever your focus is, you'll find something complementary to what you know and maybe something new here today. But I have to start with the obligatory quote by Mark Twain, and that is, "Whiskey's for drinking, water's for fighting over." And that is as true in 21st century American politics as it was in 19th century kind of gold camps where Mark Twain might have spent some time. A little bit of a roadmap of where we're going. One thing geographers do is they look at how things change through space and time. So we'll have a spatiotemporal look at the patterns of precipitation within California. So what are we starting with as our natural water resources? And I'll explore a little bit of the question of LA as a desert. And you may have a feeling about if LA is a desert or not. There may be some emotions tied behind the analysis of whether or not LA is a desert, but we'll evaluate that. We'll look back a little bit in the last 100 years at how we've changed what downhill is. And what I mean by that is when I ask students what direction does water flow, they like to say north. They like to try to be more specific than they need to be, but water flows downhill. And in California, we've changed where downhill is over the last 100 years. And the water in the background of this photo at the southern end of the San Joaquin Valley is actually being pumped up Wheeler Ridge. So it's perhaps the highest elevation relief in the world that water is pumped up instead of letting flow down. And then I'll drop a few breadcrumbs as to what the next 100 years might hold. And I just chose 100 years arbitrarily since our moving and our kind of re-engineering of the natural water system in California has been widespread over the last 100 years. So I'm just kind of reflecting that into the future. A map of precipitation in California shows a lot of variability from some parts in our state that get 5 inches or less of rain per year, some parts of our state that get over 100 inches of rain per year. And if you're new to analyzing physical things in California, it might look like there is a lack of structure. It might look somewhat random. What parts of the state are wetter, what parts of the state are drier. And it ends up that as a geographer, I think of there being two patterns which overlap and end up showing why we have the distribution of precipitation we do. So to take away some of the complexity, I'm going to mask out everything but the coast and show you that if you analyze rainfall along the coast of California, going from the upper northwest corner near Oregon to the south corner of our coast at the border with Mexico, you're going to find that with almost no variance, it goes from extremely wet to extremely dry. So it's a almost ridiculously smooth transition from wet to dry along our coast. And explaining why that pattern is, which once you look at the rest of the state, um, hopefully you'll still see this pattern existing, because sometimes it gets lost in some of the more complex patterns. But the reason for that is that most of our rainfall comes from mid-latitude cyclones. And mid-latitude cyclones are found where the polar jet stream is. And just due to turbulence within it, it's more likely to be found further north than where we are. And as you move progressively south in the state, you're going to find places that are less and less likely to have the polar jet stream hit them during the winter. So as we look at a map of precipitation along the coast, we're essentially looking at a probability map of where is the jet stream. Jet stream is most likely to be up near the Oregon border. And as you move south, it's less likely to have a large enough wave to travel that far south. So that's the first physical control on our patterns. And the second one you can see if you take a slice from west to east at a couple of different places within our state. So there's one further north, kind of in the mid-Sierra, and there's one in the southern Sierra. But either way, they reveal the same pattern, if just to different extents. And that is when air masses and when storm systems come from the Pacific Ocean, they initially encounter our California coast ranges. And that lifting that they encounter when they hit the coast range causes a moderate amount of precipitation. When air sinks down on the east side of those coast ranges, it creates a rain shadow because of the heating and compressing that happens. So immediately inland from those mountain ranges, it's drier. And then further inland, those storms or air masses are going to encounter the Sierra Nevada, a much larger, more formidable barrier. And when they go up and over the Sierra Nevada, they produce even more rain and snow, followed by a rain shadow on their eastern side. So that west-east pattern is visible almost everywhere in the state, controlled by our terrain. And when you look again at a map of California, hopefully you're seeing this north-south gradient, most apparent along the coast, and this west to east gradient where the terrain itself is causing patterns of precipitation. So given this, this is kind of the backdrop of what kind of natural precipitation we have to work with. If you're looking down at the Los Angeles basin, you may notice that although we're not one of the darker red areas, we're certainly not one of the wetter areas of our state. So we live in a region with some water, with some limitations in our water availability. And I want to look at one of the tools of geographers to assess what is an average year in a given location. So this is a climograph which shows both air temperature and precipitation over the course of a year. And it's got two vertical axes, one to represent each of those characteristics. Now, through the year from January through December, the red line here is going to connect together the average temperatures you would find through Los Angeles. And the reason why a smooth line is used is because air temperature, even if it goes from a low temperature to a high temperature, is going to cross between and cross through all of the values in between. So you would never have a discontinuity in an air temperature record. You would always have a smooth connection between high and low values. And then more interesting for Los Angeles is looking at the distribution of monthly precipitation. And that means collecting and cataloging all of the rainfall that falls on average within a given month. And this is represented by the bars because the bars represent a physical amount of rain, kind of metaphorical to what you might capture in a rain gauge. And its axis starts at 0, indicating that the actual relative size of these bars is proportional to the amount of rain they represent. So if April tends to get just under an inch, that means it is March's bar is 2.5 times larger because it's about 2.5 inches. So we can see proportional amounts. And one thing you should be struck with in Los Angeles is that our summer is noted for having kind of the coincidence of two patterns. One is it's our hottest time of year, which isn't that surprising, but it's also our driest time of year with respect to rainfall. And that's not true for most parts of the world. Most parts of the world get significant rainfall during the summer. And what this sets up in our Mediterranean climate is a summer and early fall period, which is critically dry. So when it's the hottest, when vegetation, when people, when agriculture needs water the most, there's not much available in our natural supply. And if you were to add up the bars of each of these months to come up with what's our average over the course of a year, we get about 15 inches of rain per year in Los Angeles. And although it's not a perfect definition, a desert is often seen as starting with um, having rainfall totaling less than 10 inches of rain per year. So Los Angeles at 15 inches, depending on how you're viewing these statistics, you might view that as healthily above that 10-inch cutoff. Um, but the fact that we have a hot, dry summer means we still have some of the um, water limitations that are kind of characterized in deserts as well. One thing that our climate, which has this very predictable pattern of our summers are drier than our winters, sometimes that misleads people into thinking that because there's some predictability in this seasonality, that means we always get 15 inches of rain per year. A couple of years ago, we got much more than that. And depending on where you were measuring, we could have gotten around 30 inches of rain. This individual these bar graphs that represent the larger figure here are actually on the same scale as this shrunken down climate graph over here. So I took the previous figure, shrunk it down so 4 inches is the top of this figure, which matches with 4 inches on the larger graph to show you that in the winter of 2023, we got approximately 9 inches of rain in January and in February. So multiples of what we typically get. And that's one of the characteristics of Southern California you may be aware of. It's kind of woven into our mythology that we have droughts and we have floods. And I like to spend just a few minutes kind of pulling apart statistically what our average of 15 inches really represents to reality. And if you look at a very long-term record of over 100 different water years graphed together, the red dotted line here represents 15 inches, the average, and then each individual year represents a bar graph. And without showing any complex statistics, just looking at this, you can see that quite often we're well below 15 inches of rain per year. Occasionally we're well above, sometimes double 15 inches of rain per year. And it looks like the least likely thing is to actually hit exactly 15 inches of rain per year. So through time, our rainfall is quite variable. In order to make a little bit more sense of this, instead of going through time, I'm going to show you these values arranged from our highest annual totals to our lowest annual totals. And what it shows is some years we get as much rain as Portland, Oregon does, 35 inches or so. 29% of the time, we've gotten within 3 inches of our average. So that's less than 30% of the time are we within 3 inches above or below our average. So thinking of our average as what we can expect is actually not true, right? 70% of the time, we get something either much higher or much lower than our average. And 28% of the time, we get the rainfall you would associate with a desert. So our distribution, kind of our range of how much rainfall we can get each year and how often we encounter very low or very high, means that the average is one of the least useful things to explain kind of our current experiences of any given year in Los Angeles. Ooh. Before I show you the next slide, I want you to think for just a moment. I mentioned some of our mythology is that Los Angeles has both wet years and dry years. And do you think that that behavior of having wet years and dry years that are outside of our average, do you think that's kind of a unique pattern for Los Angeles, or is everywhere kind of like that? Does everywhere in the US have wet years and dry years? It's just that Angelenos like to kind of complain and make their situation seem unique. Let's look at a map that shows rainfall not by total amount, but by variability each year. So on this map, the low values, which are kind of like the peach or pink, low values are places where there's not that much statistical difference between a wet year and a dry year. There's still wet years and dry years. They're just pretty similar statistically. The yellow places are places that have some variability between what a wet year is and a dry year is. And then the greens and into the blues are the places with the most extreme differences statistically between what a wet year and a dry year is. So what I find interesting about this is it's almost as if California was carved out based on, let's take the part of the United States that has the most variable rainfall year to year and make it all one big state. And that's essentially what we have over in California. So if you feel like our wet years and our dry years are drastically different, it's not just your feeling, it's statistically valid that we have a different relationship with floods and droughts than the rest of the country does. And I want to show you what can happen during one really large rainstorm, since we know that our wet and our dry are statistically different than wet and dry are in some other places. And this is a hand-drawn figure representing a 2-day rainstorm in 1978 that brought, if you can read the fuzzy numbers here, over 16 inches of rain or the equivalent of rain and snow to the San Gabriel Mountains. So that would be a year's worth of Los Angeles precipitation falling in the local mountains in one day, 1 or 2 days. And you might imagine that that could cause some trouble. Now, what causes this much rain to fall in one place? Since we already saw that the jet stream is more likely to be further north of us, less likely to be down in this part of the state. Well, storms that have really just been described in the last couple of decades called atmospheric rivers can point a plume of water vapor essentially right at a portion of the state and direct it like a fire hose. And when this happens, one location can get a lot more precipitation than the areas around it. So in this 1978 storm, a few things happened, including the highlighted areas here. Flash floods swept cars off highways, freed 3 dangerous lions from their cages, later shot by sheriff's deputies, and washed at least 30 corpses from their graves near the city of Tahunga. So people in other parts of the country who try to say we exaggerate when it rains a lot do not have lions running around and corpses coming from graves and things like that during our extreme rainstorm. So this is a little bit of evidence that we live in a unique part of the world. And if you're with me, by the way, once they're removed from the graves, they're zombies. So that's just that would be my adjustment I would make to this. So now that maybe you've got a different appreciation for the patterns of rainfall, both throughout our state and how it varies through time, I want to compare that same map on the left with a map of our population on the right. And it should pop out that California does not have uniform population. Our 40 million people are clustered in a couple of very concentrated urban areas. And the largest of those urban areas, LA Orange County and San Diego, is in a part of the state with very little rainfall compared to some other parts of the state, like our North Coast or Sierra Nevada. So this sets up an issue where supply and demand don't match up within our state. And over the last 100 years, it's been the work of engineers and resource managers to take some of that water from within our state or that originates outside of our state and route it so that food can be grown and millions of people can live in areas which don't have enough water naturally to support all of our current demands. So I'm going to mention a few of the major places that Los Angeles gets water from, rather than just water that falls as rain or snow that melts off our local mountains. I'm going to talk about where water comes in from outside of our region. Just before I do that, though, I want to mention one way of breaking down where does that water go that falls is you can kind of think of 3 buckets that either could naturally happen or humans could direct water to go into. And one bucket is for environmental uses. This means habitat for critical species. This means taken up by plants and drank by animals. And then there's some water that goes to agriculture to grow food and textiles. And then there's water that goes to urban areas for the 40 million people who live in California. And the size of these buckets are different. One of these buckets is 11% of the naturally available water in California. One bucket's 43%, and another bucket's 46%. So hopefully you've got kind of an idea in your mind. You might think a hunch of what number matches up with which bucket, but it may surprise you a little bit based on the way that water is talked about in California, that the largest bucket is actually the environmental bucket. So although water is highly managed in California, the single largest use are the uses that are grouped together under environmental uses. And that means that humans is kind of where we allow water to do what it would have naturally. We allow water to support critical habitat of species, which means that the two human uses of water, the water that we do consume, are vastly different amounts. So our agriculture is about 4 times as much water as we use in cities. You may want to keep this in mind next time there's a drought and you're not allowed to wash your car or shower. I'm not saying we shouldn't conserve water, but really the urban uses are the smallest use of water when you divide our uses up this way within California. This picture is in just to show that there is some local water. Our San Gabriel Mountains do generate runoff, but it's only enough historically for about 100,000 people. Once Los Angeles reached 100,000 people, William Mulholland started looking outside of our region to support the growth. And although we could make that water go further today than we did 100 years ago, our growth has far surpassed how many this local water could support at this point. And in the history of California, much has been written and much should be read about the history of where water comes from. So I'm just going to drop a couple bits of facts of where some of our water comes from. And the first water from outside of our region was taken from the Owens River Valley. And the Owens River is east of the Sierra Nevada, and a part of our state which itself gets very little rain or snowfall, but it does get a little bit of the snow that melts off the crest of the Sierra, draining eastward into the Owens Valley. And the narrative of this, and you're welcome to maintain this narrative, but the narrative is that Los Angeles stole the water from the farmers in the Owens Valley. And that's certainly a story you could have affirmed if you visited the Owens Valley today. My personal opinion is that the story is more complex than that. And since some of us in here have been working with environmental equity specifically this semester, I will mention that historically this area, tribes that are kind of grouped together as Paiutes would use the water, they would irrigate natural grasses. And the water was taken for those tribes by European settlers who set up homesteads and farms. And Los Angeles, under the guise of starting farming, ended up purchasing land. With it came water rights. And Fred Eaton, the former mayor of Los Angeles, and William Mulholland, they kind of conspired to purchase water rights from homesteaders and farmers to then divert that water into an aqueduct that led to Los Angeles. And I think it's, at least the way I state it, is we didn't steal the water from the Owens Valley. We bought the water from the people who stole the water from the Paiutes. So whether or not that makes us more or less responsible, rounding off a few corners, that's a little bit of the story. So we take water from the Owens Valley, and it is sent into 2 aqueducts that were designed and built by William Mulholland. Now, if you're in school, William Mulholland, part of his career is a story of how you can be an engineer without an engineering degree. He was self-taught. He designed this aqueduct, which is actually sending water up the hill in Jawbone Canyon. So the water is going from the foreground into the distance. And in order to go up that hill, it's a gravity siphon. So it ends up lower than it started. And gravity and hydraulic pressure are pulling the water up this mountain. So he had some successes. It is still a functional aqueduct over 100 years later. And he also had one major disaster, the St. Francis Dam. If you read about that, it's the worst dam disaster in US history. The self-taught engineer also thought he could build a dam without proper engineering degrees. So William Mulholland has some wins and some losses in the history of Southern California. But we still use his aqueduct 100 years later. I would say most importantly, and a lot of historians say most importantly, this water project opened up sort of a manifest destiny for Southern California. If we saw water somewhere that wasn't being used by someone, we could take it. If we saw water that was being used by someone, we could buy or finagle the rights to it. So it meant that we didn't have to live within our local means of how much water is naturally available in California. And the next major place we brought water in was from the Colorado River. Now, the Colorado River is a much larger river, much larger basin. And in order to get the water from it, there weren't just some families of farmers we had to trick, but there's 7 states and another country involved in negotiating the water from this source. It actually never flows through California as a river. It forms our border with Arizona, but it does start as far north as Wyoming and flows and gathers water from snowmelt from the Rocky Mountains. If you like civics, then the Colorado water law is a really fascinating part of civics and government law and policy. It would take many chapters and many books to fully understand it. But a couple take homes of the Colorado River, this really large, important river flowing through the Mojave Sonoran Desert area, is that all of our agreements to use the water overestimate the amount of water in the river. So the amount of water is 110% allocated. And that's as if you just signed up for subscription services that added up to 110% of your income. It wouldn't work long term. And similarly, we have some resource issues with this. The water law, which involves agreements between states, Supreme Court cases, compact signs, that law allocates the largest amount of water to California. So California, which contributes no water to it, which only has this river serve our border with Arizona, which is shown in this photo here, gets more water than any other state from it. And for decades and decades, we were taking more than our legal allotment. So from California and Southern California perspective, this is great. There's this source of water and we take more than everyone, and we even take more than we're allowed. And we really don't consider the needs of others, including Mexico has often been overlooked. The river historically would have flowed into Mexico, and now it only does when there is a concerted effort between the US and Mexico to release a short pulse of water just for ecological purposes, but more for just a demonstration that it can, when given the opportunity, still flow to the river, still flow to the ocean. So this required us to build some dams. This is Glen Canyon Dam above the Grand Canyon. I should mention that many of the landscapes that have been altered by damming and diverting the Colorado, like Rainbow Bridge here, were important for thousands of years for Native American cultures who really have not been involved in negotiating and distributing the water from the Colorado. And one side chapter I won't go into in detail, but we now know, based on tree ring data from bristlecone pines, the oldest living things, which are 5,000 years old, we now know from analyzing those tree rings that the 3-year period in the 1920s that was chosen to decide how much water is in the Colorado, that 3 years was the wettest 3 years of the last 500 years. So if we use this kind of paycheck metaphor, it's like if you had a job for 500 years and you chose your 3 best paying years ever, like you're in sales, right? And your salary is all over the place, but you chose your 3 best paying years ever to decide to use that amount of money to base your expenses on. So we are severely taxing the Colorado system. And I have to acknowledge that as a geographer, there's such a wide scope to the things I find important that sometimes there's not enough time to go into detail. So I understand that the Colorado River could be talked about for weeks, and that was like 3 minutes saying, here's the Colorado, we use some of its water. So I apologize for the brevity of some really complex things, but I want to try to cover a little bit more of where all of our water comes from. So there's one major source of water within California, and that is the water draining off the western slope of the Sierra Nevada, just due to the topography of the state, will naturally travel and funnel towards San Francisco Bay. And from an engineering perspective, this is actually great because there are dozens of rivers, and yet they all funnel towards the delta of the Sacramento and San Joaquin rivers. So it's a great place to intercept water, to build infrastructure, to then pump it to where you need it. And that's what we did within the state of California. And this allows a little bit less conflict because there aren't other states involved. This system to dam up a number of rivers, to build aqueducts, to build pumps, to distribute water around our state to where it's needed, has proved very useful in the building of agriculture and cities within California. And what's shown is the Central Valley Project, which supports agriculture. There's also the State Water Project, which supports urban populations, but they're very similar in that they're capturing water that would naturally flow from the Sierra Nevada to the San Francisco Bay estuary. But now much of that is pumped out of the bay to farms and cities. This is the California Aqueduct, which is part of this system. And a little bit of the ecological impacts from this are that wetlands in the Central Valley have been nearly eliminated. And there's a fish shown at the bottom right. I know that looks like a salmon or a mackerel or something huge. It's a delta smelt. It's a fish that's about 2 inches wide, 2 inches long. And it is both, its habitat is replaced by salt water in the delta, and it's sucked into the pumps and killed. So it's now an endangered species whose critical habitat has had to be enforced by federal judges and state judges. And so this small fish has limited the flexibility we have as humans to engineer and move water around our state. It's just kind of one symbol of we've taken so much from a system and changed the system so much that we're no longer able to continue as we have for the last few decades. There's currently plans to change the Endangered Species Act so that critical habitat wouldn't be considered or protected under the act, but only killing of an animal. If this is true, the double-edged sword is that in one hand, it would be bad for our ecology in California. On the other hand, it would free up our water resources to use water for urban and agriculture. So I know I mentioned a few places our water comes from, and I just want to highlight a couple similarities. And the similarities are that agriculture, municipal, and habitat uses are kind of balanced from all those sources. And by balance, that doesn't mean that natural habitats get as much water as they need. It doesn't mean that every farmer in the state gets as much water as they need, but it does mean, in truth, that our water is distributed, and those three uses of water are accommodated and considered. But from each one of those sources, think of California in 2025. We have over 40 million people living here. In each case, we can take less water than we have historically. From the Owens River, we were sued. There's a Supreme Court case that limits the amount of water we can take from the creeks entering the Owens River. From the Colorado River, we historically took more than our 4.4 million acre feet allotment. The Supreme Court, Arizona versus California, has required us to limit ourselves to 4.4 million acre feet. The Bay Delta, there are endangered species that limit and reduce the amount of water we can take. So in 2025, all of those three sources are reduced from their historical amounts simply due to the law and legality. We're not talking even yet about climate change that threatens the viability of those sources through time. We're talking due to overuse and basically due to Southern California taking more than they should have, we now have to support more people on less water. And I find it ironic sometimes that the indigenous use of water in California has almost no value from the eyes of the laws that kind of set up our water allocation announcements, even though there's a number of Sierra Nevada rivers named after tribes like the Mokelumne, the Cosumnes, Tuolumne. They're named after historical tribes, and yet they are really just distributed to farms and cities and species when required. Within a lot of our country, I know you're aware of political polarization, and politics in the last 10 years especially has kind of ramped up our tribalism. In California, a state that's in recent decades been considered a blue state and a really strong blue state, the polarization of water and the allocation of water to farmers and supplying water for endangered species instead of farmers, that's really been a ground zero for a birth of more polarization in California than I think we saw a few decades ago. And if California is to become purple or red, I think that water and our distribution of it and the story behind it and the mistruths of what we do with water in California, I think could be responsible for that eventually. Um, During his podcast last summer, now President Donald Trump spoke a lot about water in California, and much of it didn't seem to understand kind of the balancing act we do. He talked about touring the Central Valley by Devin Nunes and other politicians and being shown that we no longer allow agriculture in California because of endangered species. And there was no mention of the fact that 9 of the 10 top agricultural counties in the whole country are in California. Um, so it's true that we don't give every drop of water to agriculture, but it's also true we don't give every drop of water to cities or every drop of water for the environment. And I think that our water in California, even before it was used politically after our recent fires, I think water in California is really a way that those who thrive on polarization have seen an inroad to California. I do want to talk a little bit about climate change and what it might mean for our future. And I'm going to present 2 winters here. And in the past, we've always had variability in winters. We've had some warm winters, we've had some cool winters. And if a storm hits the Sierra Nevada or another part of the state that kind of is responsible for providing a lot of our water, what happens in a warm winter and a cool winter are going to be different. And the biggest difference is the level of the snow line. In a warm winter, we're going to have more rain, less snow. In a cool winter, we're going to have more snow and less rain. And this is significant, even if the same amount of water arrives in a warm or a cool winter. This is significant because when water stays frozen on a mountain for months, like it does in cold years in the Sierra Nevada, it gives water resource managers a lot more flexibility of how to use and distribute that water in California. And I want to show what happens when this warm winter and cool winter progress a few months into a warm spring and a cool spring. So note, especially the snowpack on the warm winter up top here. When we move to a warm spring, that small snowpack melts essentially as soon as it warms up, that small snowpack melts. And the cool spring, not only is there more snow to melt, but it takes months for the snowpack to ripen. Snow doesn't just melt when the air temperature gets above freezing. Snow melts when the entire snowpack gets to the melting point, and then extra latent heat is added to that snowpack. And because of this, the difference between is our snowpack gone in March versus is our snowpack still there at the end of June, beginning of July, is what the top versus the bottom image show. And as you can guess, maybe you can guess that more of our years lately have been like the warm year and less like the cool year. And I want to show a way to use water to kind of verify some things that we observe. You know that there are more than one way always to interpret data. So I'm going to show you a slide here that you can look at either of the multi-decade periods. So it's a multi-decade period showing what a lot of us view as the signature of global warming, the signature of climate change on the Western United States. Anywhere that has a red dot is a long-term meteorological station, which has shown a warming trend over these multi-decade periods. Anywhere that has a blue dot represents a place that's had a cooling trend, and the size of the dot represents what is the magnitude. So a big red dot is a lot of warming, a big blue dot is a lot of cooling, and the smaller dots represent a small amount of cooling or warming. So you notice throughout the Western United States that although there are a few stations which have some cooling, it's pretty well represented by the warmer stations. So as we know from various measurements, our Western United States got warmer in the second half of the 20th century. But sometimes there's questions about maybe our instruments are wearing out, maybe our cities are getting bigger and there's an urban heat island. So I want to show how hydrology can be used to serve as another way of looking at how much change there's been to our climate. And I'm going to show a similar figure that has precipitation. And here it's not always the same stations because different measurements are taking different places, but places that have been getting drier over multi-decades are shown in red, and places that have been getting wetter are shown in the white circles. And one thing you notice about the West is that there's a mix now. While almost everywhere was getting warmer, with a few exceptions, now there's some places that have gotten wetter, some places that have gotten drier. And the final figure I want to show you is not measuring air temperature, not measuring precipitation at points, but measuring the timing of stream flow in rivers. So rivers themselves are essentially performing climatological analysis throughout the West. When a river melts is determined by how much snow fell and how much energy goes into that. So in this figure, the red dots represent river systems that have been melting earlier in the year, and blue dots represent river systems that have been melting later in the year. Now, later in the year is usually more useful for water managers. Earlier in the year is what you would expect if the warming that our thermometers is picking up represents true changes to the climate system. So what you notice in the Western United States, especially California, almost all river systems are melting earlier, some 3 weeks or more earlier in the year, which is like forcing us to spend longer and longer time without our water available. So if our water comes earlier in the year, it means we have to find something to do with it in the spring as opposed to having it available for us in the summer. And to visualize why that is, we're looking here in the southern Sierra. We're in Sequoia National Park, looking at the middle fork of the Kaweah River, another Sierra River with a native name. And we're seeing the snow on some 13,000-foot peaks. Now, down at the bottom of the canyon, you can't really see any water, but if you understand geomorphology, the shape of the land, you know that when snow melts, it goes downhill and it forms canyons. So you can believe that there's a river at the bottom of this canyon. When this river flows, like when it comes up in the spring, is determined by how much snow falls on these mountains. So essentially, here's a kind of a geographic concept. By measuring when the water flows at the bottom of this canyon in one location, you're essentially looking at how energy is integrated over this much larger watershed area. So rivers themselves, as opposed to a temperature measurement, which just tells you about one little place, studying and monitoring rivers tells you about energy over literally hundreds of square miles. And it verifies the fact that, yes, our Western United States is warming. We're going to have less flexibility with when the natural snowmelt comes. So water managers who are trying to manage 40 million people, the most productive agricultural counties in the country, and endangered species, and reduced amounts of water historically, have to deal with changes to this natural system, which our own engineering is built on the assumption that natural systems will continue to provide water in the amounts and quantity and timing that they have historically. And that's simply not true looking to the future. George, is there a time you wanted me to stop and tie it up for any questions or?
Well, if you would like to leave some room for Q&A, we have 10 more minutes, and there might be a lot of things that you've discussed that people want to follow up on. But go ahead and bring it to a close. This has
Okay.
been fascinating. Beautiful photography to boot.
Okay. And I think that every photo I've had so far has been my own, with the exception of the Delta smelt, that small fish, not my picture, but I think everything else is mine. I'm going to see if there's one more topic. Oh yeah, we're almost near the end, so that's good. I don't have and I do apologize a little bit for, I know I've kind of gone quickly with some info here, but I want to create a kind of broad and accurate enough picture. So these two, just since you mentioned photos, these two are not my own, but this is looking at Lake Powell, one of the major reservoirs on the Colorado River, many years apart to show what happened during a multi-decade drought in the West. So same location. I believe this was the 90s, and this was just a couple years ago. And you can think of reservoirs as kind of a savings account. right? If you're running over budget, if you're running a deficit on a month, you draw from your savings. And we've done that in the West. Before the West had as many people, we built up a savings account in reservoirs, and we've been extracting water from groundwater. We've been drawing down reservoirs. And until the big winter of 2023, they didn't know how they were going to continue to get water out of Lake Powell because the intake pipe, the intake valve of the dam was in danger of being dry. So this is just a little visually striking evidence of some of the complications we have in the West. I could have cropped more of this out, but I wanted to show you some of the GCM, the global circulation model projections for this century, what's going to happen by the end of the century. And the top series of figures, the top series of globes here represent temperatures. And if you notice, there is no temperature scale, what's the color for the part of the Earth that's predicted to cool? There's no color. There's no temperature scale for that because the models predict that not only is the Earth warming on average, but every square inch of the Earth is predicted to warm. We see that it's not all in the same places, more in the Arctic. But that's kind of a simple story of the Earth is getting warmer, everywhere is getting warmer. But the bottom two figures show precipitation, and the red and the orange are places of the world that are predicted to become drier in coming decades, and the blues and greens are parts of the world that are predicted to become wetter in future decades. And so you notice that there's a more complex pattern here. And myself, as somebody who used to do a lot of hydroecological modeling, it's great to look at models, but there's something we say as modelers, and that is that all models are wrong, some models are useful, right? So neither one of these is an accurate picture of what the future will be like, but it's a picture of what we think what we think the future will be like, given what we know now. So it's still a useful thing to look at. And what it tells us is some parts of the world are going to get drier, some parts are going to get wetter, as far as we know. And the boundary between wetter and drier is right about where we are. So if warming makes things more complicated by hurrying up the snowmelt, the fact that we're right on this boundary of are we going to get wetter, are we going to get drier, should concern you even more in California. And the historical statistics showing that rainfall in California is highly variable, at the simplest level means that increased variability in the system is likely to affect us a lot. So none of the model projections really say anything good about the stability of our predictions for water in California in the future. Desalination is something which certainly should be mandatory to learn about in an environmental science class or geography class. All I will do for now is to give it the short little bullet point of saying taking the salt out of water and providing municipal populations with clean water is a great idea that right now uses a lot of electricity and costs us a lot of money. And that's why we don't do it much. With that idea, I'd like to expand just for a minute beyond water and say that any use of water is actually also a use of energy or a source of energy. And any source or use of energy is also an expression of water. And this idea is called the water energy nexus. The cartoon shown here shows different fluxes for water and energy. But if I could just take one of these, point out here is a desalination plant. And the story here is that if we had more clean energy, well, then we could create water. And one corollary to that is the dam over here. If we have more water, we can create more energy. So that advances and breakthroughs in either water quality, quantity, or energy can help solve the related kind of corollary problem. And that thinking about where we live as being a place that's limited in water is useful in some ways, but water is not the only thing. It's not the only requirement for human habitation or sustainability. And I've got an image here which is going to show energy use per capita by state. So I want you to think for a second. Where do you think California is? Does California use a lot or little energy use per person? And the top 10 list here is going to be the states that use the most energy per person. And I've got a prize here. I'll just toss through the screen. So whoever tells me where in the top 10 they see California, unmute and tell me where California is in the top 10. Okay, so we're not in the top 10. We don't use, and these statistics are a little bit older, but any year the list shuffles a little bit. California is actually a little further down the list because District of Columbia is in here. There's 51 states, and in 2010, California actually ranked 51st. So we use the least electricity per person, which, if that's surprising, part of the reason is we have 40 million people. So our energy use, electricity use is great, but our urban environment, our moderate climate does lead us to being relatively efficient. I'm not going to think of this as justification for bringing in water from outside of our region, for causing endangered species, for getting sued by other states by the amount of water we use. But I am going to say that thinking about suitability of, is Southern California a suitable place to live? Is it a suitable place to have large populations of people? Is more than just water availability. One thing I think ironic is that Wyoming is where the Colorado River starts. There's people in Wyoming who are cursing California for taking their water, and yet they're using much more electricity per person. So if anything, perhaps it's water and energy are both complicated. And I'll just leave a picture of a nice manicured lawn in the middle of the Mojave Desert at a Metropolitan Water District facility. So sorry if I ran out of time here. I did try to finish at the end there, but
Perfect timing, Mike.
okay.
Absolutely. MWD has a green lawn. That is incredible. Well, thank you, Mike. This has been a real eye-opener, and we have not visited this topic of California water in a very long time. If those of you visit our website, there is a tab called Teaching Resources, and you can see all the previous seminars. We haven't looked at California water since I think maybe 2023, 2021. So this really brings us up to date. And I have one question for you real quick. I know we're running out
Of
of time.
course.
But in LA, we talk a lot about two sources of water that are underutilized. One would be sustainable use of groundwater or aquifers and stormwater capture. Would that be a significant contribution to our water needs that we could then reduce our imports?
It certainly could, but I mean, historically, 100 years ago, one thing we were doing was we were pumping out groundwater, and our groundwater really isn't a separate source. Our groundwater really is rainfall and snowmelt from the San Gabriel Mountains. The San Gabriel Mountains are kind of like our barrier mountain range. So whether or not we take surface water from streams or groundwater from underground, it's more or less the same source, with one little exception I can think of, and that is some of the times that we import state water. Water is a commodity. It costs more certain times a year. And one thing we do is we import water. We buy it when it's cheaper, and then we flood fields, and it's called groundwater banking. So we buy water from outside our region, put it into our aquifers, pump it out later. You see this a lot along the 605 if you drive past those debris, those like flood control basins. But yes, stormwater capture is, if this were a talk about what can Los Angeles do to become more efficient, stormwater capture is a great avenue to look at, because one of the things we did 100 years ago, in addition to bringing water in out of our system, is we asked engineers, what should rivers look like in order to get water out of here as quickly as possible? And they built cement trapezoids and got water out of here as quickly as possible. So yeah, rethinking that would be a great step towards supplying more of our local sources for sure.
Thank you, Michael. This has been a wonderful talk. We're now bringing this particular seminar to an end. The recording will be posted on our website for today's talk, and that will include other materials that will help in letting faculty use this material in teaching modules and insert it into your course curricula. So that is a wonderful resource for faculty to use. And I think with that, as we bring this to a close, there is a community of practice that follows this meeting, and it starts in about 2 minutes. And that would be our faculty that want to that participate in that community of practice. So I'll let Beth take over from there. I think we can probably stop the recording whenever you want, Beth. We can stop the recording.
Okay, thank you. Thank you so much, Mike.